Hi, in this video we're going to talk about ionic equations and net ionic equations and precipitation reactions. So let's start off by talking about a couple of different kinds of chemical equations. The standard chemical equation that we've been talking about up till now is what we call a molecular equation. And molecular equations are often used when someone is talking about what reactants are put together and what products are formed. And it's something that is useful when, for example, you're giving someone instructions on how to set up for a reaction. So, for example, I could say, hey, we're going to take some sodium chloride and we're going to combine it with silver nitrate. And when we do that, we're going to shuffle the anions around and we're going to make silver chloride and sodium nitrate. And so you can see how we write that as a standard molecular equation. Now, this was one of the example equations that I gave in my previous video, and you can see that both of the reactants and one of the products are aqueous, and our silver chloride is a solid. But when you're dealing with ionic compounds, or anything that dissociates in solution, it's helpful to write an ionic equation, which basically talks about the behavior of the ions in solution. So remember, when you dissolve an ionic compound in solution, that ionic compound dissociates into component ions. As you dissolve the solid sodium chloride in water, and as you dissolve the solid silver nitrate in water to make your aqueous solutions, those end up as separate ions. And then the silver chloride comes together. Now, what happens to our sodium nitrate? Remember, it stays aqueous, if you remember our original molecular equation, which means it's still dissociated at the end of the reaction. Only the sodium chloride, which is solid, remains as a unit. So now I've written the ionic equation here, and you can see that in the reactant half of the equation, we have sodium and chloride dissociated, so they're listed separately. We have silver and nitrate dissociated, so they're listed separately. And then on the product side, we have sodium and nitrate, which are aqueous, so they're listed separately. And then we have silver chloride, which is a solid, so it's not dissociated, and therefore it is listed as a unit. Ionic compounds dissolve in water because they can break up into ions. When you get a reaction product that forms an ionic compound that is not soluble in water, in other words, that becomes a solid instead of staying as separate dissociated ions, that is what we call a precipitate. And any reaction which forms a precipitate, where you have soluble reactants combining to form an insoluble product, that is what we call a precipitation reaction. There are a couple of different ways to determine whether something is going to be soluble. One is very mathematical, and this is something that we're going to talk about in Chem 2. But for now, we're going to use just an approximation, things that we call solubility guidelines. Now, early in my career, when I was trying to teach these to students, they had a little bit of trouble getting a handle on what worked, and I ended up using an emoji scheme. You can see here some emojis. If you see a happy face, that means that something containing these ions will always dissolve. If you see a frowny face, that means something containing those ions will generally not dissolve. And then the straight face over here, that means sometimes they dissolve and sometimes they don't. And we'll talk about those a little more. So let's go ahead and look at the solubility guidelines. You can see I have two happy face emojis, and that's because I've broken up the cations and the anions. If you have ionic compounds with the following cations, they're always going to be soluble. First of all, everything in group 1A, so this is all the alkali metals. Now, technically, hydrogen is also in group 1A, but we're not going to count hydrogen. So you want lithium, sodium, potassium, rubidium, and cesium. Technically also francium, but francium generally does not exist in large enough quantities to really be a thing. Let's just say these 5. And then the other really soluble cation is ammonium. Now let's talk about our anions. And we basically have 3 extremely soluble anions: nitrate, perchlorate, and acetate. Now, perchlorates are a little problematic to work with, so when you want something that's soluble, it's almost always something nitrate or something acetate. Just FYI. Let's look at our straight face anions. You can see that they are usually soluble. So you can see here that we have some halogens, chlorine, bromine, and iodine. Fluorine does not fall in that category, by the way. And chlorides, bromides, and iodides are soluble unless you have them paired with very particular cations like silver or lead, or what we call mercury 1, which is a double mercury cation. Sulfates are soluble unless they're paired with strontium, barium, lead, and that weird mercury compound. Okay, now let's look at our frowny face compounds. These are frowny face anions. Everything in this box, assume it is insoluble unless you put it with a smiley face cation. So carbonates are not soluble unless you have, for example, sodium carbonate is soluble because sodium is a happy face cation. Okay? Phosphates are not soluble, but you could put them with, let's say, ammonium or potassium or sodium. So those phosphates would be soluble, but any other phosphate would be insoluble. It would precipitate out. The next 2 we see are sulfide and hydroxide. Again, these are insoluble unless they're paired with our happy face cations or these 3 cations: calcium 2+, strontium 2+, and barium 2+. And those 3 are all alkaline earths. Note that magnesium and beryllium, which are alkaline earths, those sulfides and hydroxides are not soluble. So it's just these 3 alkaline earths. Do I expect you to memorize these? No. But I will say that if you can remember that ammonium and the group 1A cations are soluble, and if you can remember nitrate and acetate as always being soluble, that usually goes a long way to remembering what's soluble and what's not. Okay, so now that we've talked about the solubility guidelines, let's look at a third kind of equation, which is a net ionic equation. I put here a series of steps for writing net ionic equations. In order to write a net ionic equation, you first have to write an ionic equation, and it's also very helpful to write the molecular equation as well. And that's what we're going to be doing for this last part of the video. So to start off, you're going to write the ionic equation, assuming that reactant ionic compounds dissociate. So usually when I'm doing this, I'm going to start off, actually I usually start off writing the reactant side of the molecular equation, and then I'm going to write the reactant side of the ionic equation. Once you do that, you're going to check the ions in solution and see if there's a cation and anion pair that could combine to form a precipitate. So that's where you're going to check your solubility guidelines. When you find a pair that precipitates out, you're going to write that precipitate as a solid on the product side. And then whatever's left is going to stay in solution as aqueous ions. At this point, you need to double check that your atoms and charges balance. And then finally, we're going to remove what we call a spectator ion. Now, what in the world is a spectator ion? So let's go back to our equation that we've been working with here. Our sodium chloride and our silver nitrate have dissociated in solution, and now everything is moving around. as things do in solution. So what can happen? Well, the sodium and chloride can come together again, but they're just going to separate because sodium chloride is soluble in water. It does not form a solid, and so anything that sticks together will quickly dissociate again. We could have the sodium and the silver come together, but both of those are positively charged, and so they're going to repel each other. Only when chloride ions and silver ions come together do we get something that actually sticks. So what about the sodium and the nitrate? Well, they can interact with other things. I didn't show it, but the nitrate could go back with the silver, but since silver nitrate is soluble, they will dissociate again. So it may happen, but it doesn't stick. In the end, there's only one thing that's permanent: silver chloride. So these spectator ions, you can think of them as spectators at a sports event. If someone follows a team and it's your pick Super Bowl, World Cup, World Series, and they're super excited that their team makes it, and they go get tickets for the finals, and they're sitting there screaming their lungs off, and they're like, we won, we won. Well, who won? Did they do something? Yeah, they did. Did it contribute to the outcome? Probably not. Don't think that spectators really have that much effect on the final outcome. So again, the sodium and the nitrate here, they might interact with the other ions, but nothing permanent is going to come of it. So that's what a spectator ion is. The spectator ions tend to be the ones that are very happy to stay in solution. So those are often going to be your smiley face, or at least your straight face ions. Let's go back to the equation we've been working with, and let's write a net ionic equation for that reaction I've been showing you. So write the reactants of the ionic equation, assuming complete dissociation. I've already done this. Here's sodium and a chloride and silver and nitrate. Check to see if any ion pairs could form precipitates. If you look at our solubility guidelines here, which I've sort of abbreviated, you can see that we have chlorides are usually soluble, but not with silver. So that tells us that silver and chloride would form a precipitate. And so we're going to write that as a solid on the product side, AgCl, and then everything else remains as an aqueous ion. Now, we're going to make sure the atoms and the charge balance. So atoms, that is just what we've always been doing. We have one sodium atom at the beginning, one sodium atom at the end, and so forth and so on. Charge, all of your charges on one side of the equation should add to whatever the atoms and charges on the other side of the equation are. So here we have +1 plus -1 from the chloride, plus 1 from the silver, plus -1 from the nitrate, so that's a total of 0. And then down here we have +1 plus -1 plus 0, so that's also a total of 0. Now we're going to remove the spectator ions, and basically what you're going to do is you're going to look at the reactant and product side, and you're going to find things that appear on both sides. So here we have sodium in both the product and reactant side. You have nitrate in both the product and the reactant side. So we're going to take those out, and what we get is this. Aqueous chloride ion plus aqueous silver ion gives us solid silver chloride. So what does the net ionic reaction tell us? It basically tells us what is actually happening that makes a difference. Is something happening with the sodium? Not really. It's just hanging out. So you may not actually care that it's in solution. All right, so what we're going to do here is practice writing the molecular, ionic, and net ionic equations for combining two soluble ionic compounds. In this first problem, we're looking at silver nitrate and sodium carbonate. So the first step tells us to write the reactants assuming that ionic compounds dissociate. And I find it easiest to write the reactants for the molecular equation first because those are given in the problem. So here we have silver nitrate and sodium carbonate. AgNO3, Na2CO3. Now, Where people run into a little trouble with this is in knowing what the formulas for those polyatomic ions are. And this is something that you possibly might want to memorize. If you're in my class, if you're watching this and you're in my class, you can look on Canvas. I have a handout with some very common polyatomic ions and their charges. If you're not in my class, check your textbook because there's probably a list in there. Once you have written the reactants for the molecular equation, that helps you write the reactants in the ionic equation. So basically, you're going to take those apart. Now, we have silver nitrate dissociating to give us silver ions and nitrate ions. We have sodium carbonate. And again, remember that we've got 2 sodiums in sodium carbonate, so we end up with 2 moles of sodium ions and a carbonate ion. All right, now we're going to check to see whether any ion pairs could form precipitates. And like I said, usually where people have the easiest time doing this is finding the ones that are the happy cations or the happy anions, the ones that really love to stay in solution. And here that's going to be nitrate and sodium. So what's left is silver and carbonate. So we're going to write the precipitates as solids on the product side. Now you'll notice when you're looking at this that silver has a +1 charge and carbonate has a -2 charge. That means we're going to need 2 silvers for every carbonate. So it's going to be Ag2CO3 plus 2 sodiums plus nitrate. And so you could see how we go right into step 4, where you have to make sure that atoms and charge balance. If we have 2 silvers in silver carbonate, that means we have to start with 2 silver ions. Now, where would we get 2 silver ions from? Well, we'd have to start with 2 atoms of silver nitrate, right? Well, if you have 2 atoms of silver nitrate in your molecular equation and they dissociate, that means you end up with 2 silvers, but it also means you end up with 2 nitrates. So now we can throw in 2 nitrates. This is why I like to do both the molecular and the ionic simultaneously, because we learn things from each of these, and so it helps you figure out each of these together. You can double check the charges now. I'm not going to do that now, but I'll just say it works out. Okay, finally, we're going to remove the spectator ions. Nitrates are on both sides, sodium's on both sides, and that's not surprising because as you can see, the spectator ions, once again, are the ones that are the happy cations and the happy anions, almost always. What's left then is going to give us our net ionic equation. 2 Ag plus CO3 2 minus, both aqueous, combine to give us silver carbonate, solid. If you're doing a precipitation reaction, you're always going to have ions on your reactant side forming a solid on your product side. Now you'll notice we've only written half of our molecular equation. What do we need to do to finish our molecular equation? Well, we know we're going to make silver carbonate. What do we have left? We also have our spectator ions, and we're going to write those as an aqueous ionic compound, 2 sodium nitrate. So here we have a molecular, an ionic, and a net ionic equation, all for the same reaction. Each of these gives us different information about the reaction that we're looking at. And I've hinted at what each of these can tell us. And so you'll see that your reading question on this material is to think about, what does each of these tell us? What does the molecular equation tell us? What does the ionic equation tell us? What does the net ionic equation tell us? Why do we write 3 separate sorts of reactions for precipitation reactions? All right, we're going to do one more example. Here we're going to combine lead 2 acetate and sodium phosphate. Again, we're going to start off by writing our reactants, assuming that our ionic compounds are going to dissociate. And I'm going to start with a molecular equation once again. Lead 2 acetate. Lead 2, remember, tells us that we have a +2 charge on lead. Acetate is always a -1. In fact, all of our happy anions are only -1 charges. So here's lead 2 acetate and sodium phosphate. Phosphates are PO4 3-, which by the way is down in our solubility guidelines down below. So now we have written our reactants in the molecular equation. Let's see what happens when we put them in solution. Lead acetate is going to break up into one lead 2+ ion and one, well, I forgot the 2, but imagine a 2 here, 2 acetates. Sodium phosphate is going to break up into 3 sodiums and 1 phosphate. Now we're going to check and see if any ion pairs could form precipitates. And again, we're going to look at what wants to stay in solution. That's always the easiest way. That would be sodium and acetate. Now, if you look at lead and phosphate, well, phosphate is definitely one of the frowny face anions, so that's going to precipitate. We need to write our precipitate as a solid on the product side. We have a +2 cation and a -3 phosphate. And sometimes people get a little confused saying, how do you put things like this together? And I'm just going to say that the easiest way to do it is to look at the charges and find the least common multiple of those charges. So we're actually thinking about the absolute value of the charge. So we have a charge of 2 and we have a charge of 3. The least common multiple of 2 and 3 is 6. And so you have to ask yourself, how many of each ion do I need in order to get to a charge of 6? Either +6 or -6. So for lead, we need 3. And for phosphate, we need 2. So we're going to have Pb3. So we're going to have 3 leads and 2 phosphates making up our ionic compound. We can write that in our ionic compound. And now we have to make sure that our atoms and charges balance. So you can see that we have 2 phosphates in our precipitate, which means we have 2 phosphates here. Where did we get those 2 phosphates from? Well, originally they came from our sodium phosphate. So we need 2 molecules of sodium phosphate in our molecular equation. Well, if you have 2 molecules of sodium phosphate and each of those molecules of sodium phosphate had 3 sodiums, you would end up with 6 sodium atoms. So that number has changed. We have 3 lead ions. So we had to start with 3 lead ions. Those lead ions originally came from lead acetate. And so we're going to need 3 molecules of lead acetate in our molecular equation. What that tells us then is that when those 3 molecules of lead acetate dissociate, we're going to end up with 3 times 2, so 6 molecules of acetate ions. So then you can also fill in the rest of the reactants in the ionic equation. Now we're going to remove the spectator ions, and once again we've got sodiums on both sides, and this time we have acetates on both sides. So those are our spectator ions. Our net ionic reaction tells us that 3 lead ions and 2 phosphate ions combine to give us lead 2 phosphate. And of course we now have to complete our molecular equation. Here's our lead phosphate, and we also have 6 moles of sodium acetate. So again, here we have our molecular, our ionic, and our net ionic equations for the combination of lead acetate and sodium phosphate to give us lead 2 phosphate. One of the reasons we like to write ionic equations is that they can help us predict precipitation reactions. This isn't the only time we use ionic equations. In fact, when we're going into the other material we're working on this week, you will see that these things come in very useful for redox reactions as well. But they are extremely useful to help us see what is changing in a reaction, and that is why we use them. I hope this was helpful, and I look forward to seeing you again soon.